Alright, welcome back. This is our fourth lesson on radical expressions, and in this lesson we are going to learn how to rationalize denominators. Now, just briefly, remember that radical expressions refer to laws of exponents. When the bases match, we add the exponents. So we add 2 plus 3 and get 5. When the bases match, I should say when the bases match and we're multiplying, we add the exponents. When the bases match and we're dividing, we subtract the exponents. 5 minus 2 gives 3. If we take power of power, we multiply the exponents, so 3 times 2 gives 6. And lastly, remember that radical expressions refer to the fourth branch of this chart, the division of exponents. So if I write the sixth root of x to the 18th, I did a brief video before this on absolute values, so hopefully you've watched that video. But even if you didn't fully understand it, what I need you to remember is that the trick that to take even exponent divided by even exponent, so in this case 18 divided by 6, even divided by even results in odd, so 18 divided by 6 gives 3. If you have even divided by even resulting in odd, you end up with absolute value, except for this case. So I need you guys to remember that the square root of x squared, and this is on the test, is equal to the absolute value of x, versus the square root of x multiplied by the square root of x, is the square root of x squared. However, we just end up with x. So square root of x times square root of x is just x, but square root of x squared is the absolute value of x. So just go ahead and take these down almost like a definition. Now, rationalizing denominators. Okay, so rationalizing denominators is a rule of simplification. Okay, so this really comes, if you see the directions on the top of page 443, it says to simplify. Okay, now simplify means to add, subtract, multiply, and divide. Let's go ahead and write that. Simplify means to add, subtract, multiply, and divide. But there's also hidden rules that are not written in the book. So simplify means to add, subtract, multiply, and divide, but it also has some hidden rules. And the first hidden rule that we learned is that you cannot have negative exponents in the final answer. So we write no negative exponents in the final answer. Hopefully you remember this. So no negative exponents in the final answer, but there's another hidden rule that we're going to add today, that you cannot have fractional exponents in the denominator. So no fractional exponents in the denominator. You can think of this as AKA, this is the easier way to think of it, no roots. Okay, no roots in the denominator. So what happens when you see a root in the denominator? You have to get rid of it. So for instance, if we have 5 over the square root of 3, what is wrong with this? Well, the directions say to simplify. So you look at this and you say, well, there's nothing to add, there's nothing to subtract, there's not really any way to divide here, so what are we supposed to do? Well, what they mean, simplify, you're supposed to know this, that you are to what? Rationalize your denominator. Think of rationalize your denominator as specific directions. And what do these directions mean? The directions mean to what? Get rid of the roots. Okay, so get rid of the roots. Get rid of the roots. In the denominator. So we're going to get rid of the square root of 3 in the denominator. And how do we do this? Well, I'm just going to make this very brief and to the point. So we have to create a pair. Notice that our index is 2. We have to create 2 3s so that we can take out a group. How many 3s do we have? We just have 1. So what we need to do is we need to multiply by another root 3. What this will do is this will create 2 3s. And if we create 2 3s, we can take out a pair. Now, if we multiply the bottom by root 3, we also have to multiply the top by root 3. Reminding you, if you have a fraction, say 4 over, let's do this. Yeah, that's fine. 4 over 2. Okay, so 4 over 2 is equivalent to what number? We know that the correct answer is what? We know that the correct answer is 2. Okay, if we multiply the bottom of this fraction by 3, what do we have to also do to the top to keep the answer the same? We can't change the value of 4 over 2. So if we multiply the bottom by 3, we also have to multiply the top by 3. What is 3 divided by 3? 3 divided by 3 is 1. So if we take 2 and multiply by 1, we still get 2. So notice, we're going to multiply our top, multiply our bottom. 4 times 3 is 12. 2 times 3 is 6. Is 12 divided by 6 still 2? Yes, it is. So as long as we multiply top and bottom by the same thing, we're not changing the value of what we started with. Now, so what we had was 1 3. Since the index was 2, we needed a pair. We needed 2 3s. So we multiply by another root 3, and what does this create? This creates the root of how many 3's in the denominator underneath the root. Remember, we can multiply radicands, so root 2 times root 3. Can we multiply the 2 times the 3 and get the root 6? Yes, we can multiply the radicands together. However, quick reminder, can we add root 2 plus root 3? Can we add the radicands and get the root of 5? No, we cannot. This is completely wrong. So remember that root of x multiplied by root of y, this is on the test, root of x times root of y is equal to the root of x times y. However, the root of x plus the root of y is not equal to the root of x plus y. So can we multiply the radicands together? Yes. But can we add the radicands? Absolutely not. So root x times root y is the root of x times y. So if we're looking at this, root 3 times root 3 is the root of 3 squared. And on top, we're just going to glue this together. 5 times root 3 is 5 root 3. Now, what is the root of 3 squared? Notice we have a pair of 3's. We can take them out, and we end up with just a 3 on the outside, nothing left under the root, so we don't write it. And on top, we have a 5 root 3. Look at the final answer. Question, is the root out of the denominator? Yes. I think of this as taking the root out of the denominator and putting it in the numerator. So we get the root out of the denominator, we have successfully simplified the problem. There's another way to think of this. 5 over root 3, if you establish the fact that you only have 1 3, but you need a total of 2, you realize you have to multiply by a root 3 and a root 3, top and bottom by the same thing. We end up with a 5 root 3 on top. Another way of thinking of the denominator is root 3 times root 3 is the root of 9. And the root of 9 is just what? The root of 9 is just 3. So we end up with 5 root 3 over 3. But I don't like you guys writing the root of 9 on your paper. Rather, remember, what is the root of 2 multiplied by the root of 2? This is the root of 4, which is just 2. We get tired of writing this. So when you write root 2 times root 2, remember that the roots cancel each other out. Root 2 times root 2 is just 2. Root 3, this has to become automatic. Root 3 times root 3 is just, the roots cancel out, we just get 3. The root of 5 times the root of 5, the roots cancel out, we just get 5. So, I like thinking of it this way. Rather, think of the root of 3 times the root of 3, the root cancels out and we just get 3. 5 times root 3 is 5 root 3, and I think this shows you the basic concept of how to rationalize the denominator. So what does rationalize the denominator mean? It means what? Get rid of the roots in the denominator. Now, let me show you another example. So for instance, if I give you the example 5 over the square root of x. Okay, so now you look at your denominator. What do we see? What's wrong with this? You're asked to simplify. You immediately see there's a radical in the denominator, so you've got to get that radical out of there. And how do we get the radical out? Well, we ask ourselves, how many x's do we need total? What is our index? Our index is 2, so we need a total of 2 x's in order for a group to come out. So if we need a total of 2 x's, but we only have 1, how many more do we need? Well, we need 1 more x. So we're going to multiply by a root x and a root x, and what is this going to create in the denominator? Root x times root x gives the root of x squared, and on top we get 5 root x. Okay, so we get the root of x squared, and remember, root x times root x does not get absolute value, so we just get x. So root x squared, root x times root x, you can think of this as taking a pair of x's out, giving just x, or you can think of this as root x times root x, the root cancels out, leaving just x. And on top we have 5 root x, and we're done. Now let's look at this example. 5 over the cubed root of x. So in this example we have an index of 3. So if we have an index of 3, in order to take a group out, to get rid of the root in the denominator, we need a total of how many x's to take a group out? We need 3. So if we need 3 x's, but we only have 1 x, how many more x's do we need? Well, we need 2 more x's. Now, you have to multiply by a root that has the same index. Since this is an index of 3, we're going to multiply by a cubed root. This is going to be cubed, can't, let me do that again. So we're going to multiply by cubed root on the bottom and cubed root on top. We have 1 x, we need a total of 2 more x's to create a group of 3. So we're going to multiply by the cubed root of x squared, and the cubed root of x squared. Notice we had 1x, we're multiplying by 2 more. This creates a total of the cubed root of x to the third, or a total of 3x's now in the denominator. Remember, we can multiply the radicands together. And on top, we just glue it together. So we end up with 5 cubed root of x squared. Now on the bottom, can we take a group of 3x's out? Yes. Our final answer is 5 cubed root of x squared over, we take a group of 3x's out, we just have now an x. Have we successfully gotten the root out of the denominator? Yes. Okay, so is this fully simplified? Yes. What is this process called? Getting the root out of the denominator. The process of getting the root out of the denominator is called what? Rationalizing the denominator. Now on the test, I may not actually write the directions rationalize the denominator. I may just write the word simplify. So your directions on the test, the assumption is that you're supposed to know these directions. So on the test, if I write simplify, you understand that within the word simplify, what rule is implied. If I say simplify on the test, I'm assuming that you know that simplify means you have to rationalize all denominators. Or if you ever have a root appear in a denominator, you have to get rid of it. Now, let's look at the book for some problems. All right, so let's look at some examples in the book, because the examples in the book are a little different. So we're going to look at the odd examples given on page 443. So we are on page 443, and we're looking at number 3. Okay, so example 3, or problem 3, is the square root of c to the 5th over the square root of d to the 9th. The problems in the book are a little bit harder. Now, well, I shouldn't say harder. They're just a little, you have to think a little bit more. You have a total of how many d's in the denominator? I should say this first, maybe. Okay, we have to do what? Rationalize all denominators. That means get rid of our roots. What do we have in the denominator? We have what? A square root in the denominator. Are we worried about the root up top? No, we're just worried about the root down here. So the question is, what is our index? Well, our index is 2. This means that we need a perfect set of pairs to come out. So we want to take groups of what? We want to take groups of 2. Now, you cannot take any d's out. I should say we cannot reduce the number of d's that are already here. We can only put more d's in there. So I'm asking, how many more d's do we need to create a perfect set of groups of 2? Well, if we have 9 d's, how many more d's? And you can put as many in as you want, but I tell students, put the smallest amount in there. Try not to put very many. Okay, put the least possible. Okay, so if you have 9 d's, how many more d's do you need to create a perfect set of groups of 2? Well, hopefully you say you only need 1 more d. Because if you put 1 more d in, you have a total of 10 d's. Okay, so 1 more d, root of 1 more d, notice. We now have on top the root of c to the 5th d. Go ahead and put your variables in alphabetical order. Over now the root of d to the 10th. So do not put, you only need 1 more d. You don't need to put in 5 more d's, but just 1 more d will take care of this. Put the least number in possible. So you have 10 d's. Question, can we take groups of 2 out? Yes. Okay, so if we have 10 d's and we take out groups of 2, how many groups of 2 are there in 10? Well, hopefully you say 5. You can also just take 10 and divide by the index 2. So we end up with d to the 5th. And on top, notice, do we have groups that can come out on top? Yes, we have 5 c's. We can take out a total of 2 groups of 2. So we end up with 2 groups of 2 coming out, giving c squared. And what's left under the root? We have cd. Okay, so c squared root of cd over d to the 5th is the final answer. Have we successfully gotten the root out of the denominator? Yes. Now, on the next problem, let's look at number 23. Number 23 says the square root of 7x over 10y to the third. Okay, in this case, this is a little different. So here you see a square root. You see a square root of an entire fraction. Notice on the first problem, the roots were independent. They were broken apart. My question is the square root of 7x over 10y cubed the same as the square root of 7x over the square root of 10y cubed? And the answer is yes. Can we take a radical and break it apart over the numerator and the denominator? Yes, we can, and I'm going to answer why right here. So I'm going to erase this. Remembering laws of exponents. I want you guys to remember that the square root of x is equal to x to the 1/2 power. The cubed root of x is equal to x to the 1/3 power. The fourth root of x is equal to x to the 1/4 power. Now, so if I write here, if I write quantity x over y squared, we've already established, do exponents distribute over the operation division? Yes, they do. So we say that this is x squared over what? Y squared. Okay, so, well, maybe before I say this, let's start with multiplication. xy quantity squared. Do exponents distribute over the operation multiplication? Yes, they do. This is what? xy times xy. So we end up with what? X squared, y squared. So we just square the x, square the y. What about x over y squared? Do exponents distribute over division the same way that they distribute over multiplication? Yes, because division is the same as multiplication. So this is what? X squared over y squared. So we can square the x, square the y. Now, what about the square root of x over y? Okay, so if we look at the square root of x over y, isn't this the same as x over y to the 1/2 power? And the answer is yes. Now, can the exponent distribute over division? Yes, it can. So we end up with x to the 1/2 over y to the 1/2. So we see that since radicals refer to exponents, the square root refers to the exponent 1/2. We're looking at this, you have to see this as an exponent. And this exponent distributes over division. So if we have 1/2 power, we end up with x to the 1/2 over y to the 1/2, which is the square root of x over the square root of y. So notice, if we have the root of a fraction, can we break this up into individual roots? Yes, we can. Why? Because exponents distribute over what operation? Exponents distribute over division. Now, once we get here, we're going to ask the question, all right, we need we need groups of 2. All right, so we need pairs. Now, the question is, how many 10s do we have? Well, hopefully you say we have 1 10, and how many more 10s do we need to create a group of 2? Well, if we have 1, we need 1 more. So we're going to multiply by a root, a square root. We're going to need 1 more 10 to create 2 10s, and we have 3 y's. So what is the least number of y's that we need to create a perfect set of groups of 2? Well, if we have 3, we only need 1 more y. 1 more y will create a total of 4 y's, and that is 2 groups of 2. So we're going to multiply by 10y, 10y. On top, we end up multiplying. Remember, we can multiply the radicands. 7 times 10 is 70 xy. And on bottom, we end up with the square root of what? 2 10s make 10 squared. And y cubed times y, remember we add the exponents, this is y to the 4th, which is the same as the square root of 70xy over, take a pair of 10s out, we get what? A 10. Take 2 pairs of y out, or take 4 and divide by the index 2, we end up with y squared. Notice, have we successfully gotten the radical out of the denominator? Yes. Okay, so what does this mean when we get the radical out of the denominator? What have we just done? We have successfully rationalized the denominator, so we've gotten the root out of there. This is the final answer. Now, one more thing I want to comment on. When you finish multiplying on top, you need to check your top radical and see if there are any pairs that come out. We should take the 70 and break it down. What is 70? 70 is 7 times 10. 10 is 2 times 5. We look at the 7, the 2, and the 5. We see that we only have 1 of each prime number, so there are no pairs of numbers that come out. Also, we only have 1 x and 1 y, so there are no groups that we can take out on top. This is why we stop and call this the final answer. Now, one more example. We're looking at number 25. On page 443. Okay, so number 25 says the 4th root of 7x cubed over 4b squared. Now, this is an interesting example. So we look at first the radical. If we take the 4th root of a fraction, can we split this up as the 4th root of 7x cubed over the 4th root of 4b squared? Yes, we can. Why? Because exponents distribute over what operation? Exponents distribute over what? Division. Remember that this is 7x cubed over b squared, or sorry, 4b squared, all this to the what? 4th root means 1/4 power. And we can look at this as 7x to the 3rd to the 1/4 power over 4b squared to the 1/4 power. So notice, the exponent 1/4 distributes over what? Distributes over the operation division, just like exponents distribute over the operation multiplication, remembering multiplication and division are the same thing. Now, so we end up with the fourth root of 4b squared. Now the question is, how many 4s do we need total? Well, if you say we need a total of 4 4s, we need a total of 4 4s because we want groups of 4, that's correct, but what it's going to do is it's going to create very large numbers. So what we want to do first is take the 4 and break it down. Watch this. 4 can be broken down into 2 identical numbers already. 4 is 2 times 2. So we can write this as not the fourth root of 4, but rather we can write this as the fourth root of 2 squared. And instead of looking at this as 1 4, we can look at this as 2 2s. Now, since we already have a pair of 2s and we need a total of 4, how many more do we need? Well, we only need 2 more. We also have 2 b's. How many more do we need to create a group of 4? We only need 2 more. So we're going to multiply by a fourth root and a fourth root. The index must match. If we have 2 2's, we need 2 more to create a group of 4. So we're going to multiply by 2 squared. We have 2 b's. We're going to multiply by 2 more. So we're going to multiply by b squared. So whatever we do to the bottom, we do to the top. We multiply by 2 squared, b squared. And this is going to get us to a final answer very quickly without having to do a lot of simplification at the end. We end up with the fourth root of... Now look at your groups up top. We're looking for possibilities of groups of 4 up top. How many 7's do we have? Well, we only have 1 7. How many 2's do we have? Well, we only have 2. How many b's? We have 2 b's. And how many x's? We have 3 x's. Is there a group of 4 in any of these numbers or variables? No. So we can just go ahead and glue it back together knowing that there's no group of 4 on top. Okay, so 2 squared is 4 times the 7 gives 28. We have an x cubed and a b squared. Put your variables in alphabetical order, so this is going to be b squared x to the third all over. Now, we have 2 squared times 2 squared gives what? The fourth root of now 2 to the fourth. B squared times b squared gives b to the fourth. And can we take out groups of 4? Yes, we take out groups of 4, take out groups of 4. We end up with the fourth root of 28 b squared x to the third all over. We take out a group of 4 2's, we end up with a 2. We take out a group of 4 b's, we end up with a b. And even divided by even resulting in an odd 1 in this case gets absolute value. And if you don't understand why, I recommend that you go back and watch the previous absolute value video. It comes back to the fact that b squared was even exponent in the original problem, meaning that we did not know whether b itself was positive or negative. Since we did not know whether b was positive or negative in the original problem, because b squared is already positive by nature, we did not know whether b was positive or negative. We have to assure that it's positive in the end because we have what? We have an even index of 4, and that concludes this video, and we will finish rationalizing denominators in the next video. All right, good luck with your homework, guys.